Hi, this is the second part of Lecture 6, where we are continuing discussing the design of CMOS gates. We looked at complementary complex gates, pass transistor, transmission gates, and tri-states in the previous lecture. We will tie all of these pieces in this lecture uh, or in the beginning of this lecture by trying to design a multiplexer and a 2-to-1 multiplexer, okay, where we have the output of the multiplexer is um, selection, if active selection line S will choose D, and the negative of the selection line will choose D0, SD1 or S prime D0. Now, we will design this with multiple methods, okay? The very first method we'll look at simple gates, and then we'll look at um, complex gates, and we will look at um, transmission gates. Okay, this is where we have non-restoring tri-state, and finally we will look at uh, inverting tri-state, or restoring tri-state. Okay, so if we want to design this uh, using a gates, so let's take a look here using gates. So very simple. We'll say that we need an AND gate, okay, and so here we have the selection and the inversion for the selection, okay, and here we have um, D0, and this is here D1, and then an inversion, okay, and then another NAND gate here and an inverter. Uh, I'm sorry, an OR gate, and an inverter. Okay, that will be the Y here. We can simplify uh, further this gate here, okay, um, by replacing it with just a simple NAND gate. So finally, it becomes something like this. Okay, so this is S, this is here D1, this is here D0, all right, and here is Y. Now this is using um, simple gates, and we can try to design this thing using a, uh, a complex gates, which is a little bit more involved, and as we studied, and then complex gates. Um, it means that as we have learned before, we will implement first the MOS subtree. Okay, so you can see here I have an ending here. So this is my ending of S and D0. Then I have another ending here of S prime. Now I assume that I have an inverter for S prime and D0. Oops, this should be a D1 by the way. Okay, and then the inversion of this at the PMOS sub tree. So PMOS sub tree will be okay, something like this. So this is D1 here, S, and then I'll have S0, S prime, and D0 here. Okay, and then this is inverted, so I need an inverter here to save space. I'm going to express the inverter in the logic simple, but we know how to implement it in the design. Okay, and then I have, don't forget that I need also an inverter here where I generate the S prime as well. Okay, so that is why right here. Now we can try the the transmission gates, and in the transmission gates I can do it as follows. So I can have, this is my NMOS, this is my PMOS, gain here, my NMOS, this is my PMOS, whoops, sorry, okay, and this is here D0, D1, S prime, this is S here, and this is this one here, S prime. The output, the transmission gates, is the Y itself. And then I can use the tri-states, okay, the tri-states, where I have the first tri-state here, and the second tri-state. Okay, so here's the first tri-state, and one PMOS, NMOS, this is NMOS. So the first tri-state has an input of uh, D0, and the second tri-state has an input of D1. Now, of course, the very first two here are PMOSes, and then here it is activated with S prime. The PMOS will be S, and here it is activated with S, and the PMOS will be S prime. And then the two outputs are shorted, okay, to generate the Y prime. Okay, so this would be a Y prime, and if I need the Y, I can invert it, but for now I'm going to assume I don't need to. I'm happy with the Y prime. Okay, so if we compare the two methods, we can see that um, the number of transistors vary. So here I have for this method number of transistor, here I have two. Oops. Two for the inverter, and four for the gates. Okay, and so here 4 plus 4, 12 plus 2, this is 14 transistors for this method. And here I need 1 2 3 4 plus 4, that's 8, plus 2 10, plus 2, that's 12 transistors. And for this method here I need 4 transistors, and for this method here I need 8 transistors, and if I need to invert the Y, right, then I need plus 2, and that is equal 10 transistors. So this is the number of transistors. Obviously, this is the least method in terms the least number of transistors method, and that's why it is preferred. Okay, and the transmission gates are known for they are excellent in implementing multiplexers. Okay. Okay. Now we go to the next topic in the slides, which talks about bubble design and compound gates. So we've done already some of this bubble design here, which means to simplify number of transistors right here. But let's take another example, which is uh, better in illustrating the idea. Suppose we want to design a 8 input um, AND gate. Okay, so we have multiple approaches to do this, and the very first approach is to use a large 8 input NAND gate with an inverter. That's one approach. Another approach is to use 4 input NAND gate followed by an inverter, and we have to use another level of, so this is basically an AND, 4 input AND followed by 2 input AND. This can be this can be simplified, okay, by a 2 input NOR gate. So this is the 4 input NAND gate, the 4 input NAND gate, and then this one can be simplified by 2 input NOR gate. Okay, so this is what is the bubble pushing and simplification means. So typically you use De Morgan law to do the simplification. Another way of doing it is to um, use 2 input NAND gates. Oh, sorry. And then inverter. Then here is another level of NAND gate. Okay, and this is inverted, and then here this one. Okay, so what we could do is we can simplify this by having this is replaced by 2 input NOR gate. So this becomes is my 2 input NAND gate, NAND gate, NAND gate, NAND gate. This goes to 2 input NOR gate, goes to 2 input NOR gate, okay, and then the final step of NAND gate with an inverter. So these are three methods of implementing an 8 input AND gate, and with simplification using bubble pushing. Okay, so let's go back to the slides here, and basically We have covered all of this. These are extra examples. You can consider them, going over them yourself. Very similar to what we have done here. We are not doing the logical effort, by the way, for complex gates. We are limiting our logical effort to just NAND and NORs and inverters. Okay, here comes another question of if you have a two input NAND gate and you have different arrival times for these inputs, uh, which one you would you would have the early signal, connect the early signal to A or connect the early signal to B? Okay, so if I may use a pin here, if we consider this solution where A arrives the latest, A arrives the latest, which means uh, B will arrive first and then A. Okay, if B arrives first, then this capacitance here will be discharged because B arrives early. Then, when A arrives, we have to discharge this capacitance. And to discharge this capacitance, we multiply 6C times this resistance R. Okay, and that's what he's referring to right here. However, if B arrives latest, so let's change the color of the pin here, and we use, for instance, the brown here. Okay, so this is where first we will have A and then B. If A arrives, we cannot discharge this capacitance because B is still not activating this transistor. So we will have to wait for B to arrive. Then when B arrives, the 2C will be discharged first, and then the 6C will be discharged later on. The summation of these two RCs is 6RC times R over 2 times 2C. Now, the resistance here is R over 2, and the resistance here is R over 2. So you can see that this capacitance will see R over 2. Summation is 7RC versus 6RC. So which has greater delay? This has larger delay. Okay? Okay, so which is better? Obviously, this is better, because it has less delay. So you would want to have first the earlier connected to B and then the later connected to. So you want early signal to be at the bottom and the late signal to be at the top, so that you can use this early arrival to get rid of these intermediate capacitance here and speed your final discharge of the output. Okay, so this is basically what we stated. Then what we have here in this is that we are asking ourselves the question, what would be the ideal size of a PMOS? So far in the course, we're using 2, the W over L for the PMOS equals 2. Now, what would be, so 2 is ideal for fall and rise time. But is it ideal as well for the delay? Well, what we are doing in this slide here is that we say, assume that we have a P here. And we want to find a P such that we are optimizing the delay. We are really optimizing the average delay. Okay, so the average delay, suppose here we are having we will compute the fall delay and the rise delay. Now, the fall delay, we will assume. Okay, just okay. So we'll assume that we are connecting this inverter to an identical inverter here. Okay, so this is of the same size, P and 1. Also notice that he is telling me that mu here, it is mu here, sorry, it is the ratio of the mobility for the NMOS over the mobility of the TMOS. Now, in terms of the fall delay, I know that the fall will happen through the NMOS transistor, so I multiply the resistance here, which is 1, right, times the capacitance here, which is P plus 1, P plus 1. Okay, now for the rise delay, you can see this is going to come from the PMOS. So again, the capacitance P plus 1 times the mobility divided by P. This is the ratio here, the ratio between the NMOS and the PMOS divided by the size here, P. The larger the P, the better for the rise time, but I am trying to find out the optimum P. Now the delay is you average the fall time and the rise time, so you add them and divide by 2, and you get this equation here. Now the optimum is that we have to derive with respect to P because we are optimizing P. This is the one that I'm trying to optimize. You derive and you equate with 0. You solve the equation and you get P equal square root of mu. So in the course so far for 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 rise and fall time, we have been using P equals 2, assuming that the ratio here is equal to. But for the delay, for optimum delay, P here should be square root of 2. Okay, and so now you can see based on what you want really to optimize rise and fall times or delay. For rise and fall times, P will be 2. For delay optimization, P will be square root of 2. Okay, and pretty much this is where we're going to stop. Thank you, and we'll have continue the next in part 3.